video. Going to continue on with the memory management stuff that I was working on a bit. So went on a small detour on the ASM check tool, the static analysis tool. Check out those videos if you're interested in seeing a static analysis tool for assembly written in Rust. But this video we're going back to memory allocation. So we ran into a problem with malloc, because malloc was basically just using a static memory assigned in like at assembly time. We just allocated a chunk of memory, and it wasn't actually checking to see whether that address that was being used was legit or not. And so what we did in the last video on memory was we basically worked out that we used a kind of bias function to retrieve information about the memory available in the system, along with types of stuff there is. I think it was detecting memory. Yeah, that one. There was a wiki page on osdev on how to do it, and I believe it even had, that's not the one I wanted to go to, this one here, that's not the one. So we kind of copied it from the example assembly stuff, not that one. I had it somewhere here, I thought. What did the this one here. So we kind of took this code, and I haven't cleaned it up yet, but potentially we could clean it up to fit my coding style a bit more. But this basically loads in the memory using the EH20 bars function, and it kind of goes into a structure, easier to see there, the assembly, but in assembly we do have kind of a structure, which we'll look at my code in a second. And I think, so this also kind of tells us the type of what it is, which we've kind of just printed out type of 1, 2, 2, 1. We don't really detect what those types mean, but what we're looking for is type 1 is stuff we can use and type 2 is reserved. And all the other types are basically unusable as well for our current thing. So what we're going to look for is just basically type 1 stuff and use that to basically allocate stuff to the malloc process. Now, usually this is done in other operating systems as like a kind of paging system. So if we look at, I'll just put it here. So we've got like a little structure here. So where it starts, the low and high, the length, low and high, and the type. And the function that we saw getting called before was just this dump memory map function, which goes through and basically shows the base address, the length, and the type. And I believe, we only really use the we do use the high and low. So if we run that again, we can kind of see the base starts there, it's got this length, type is that, and then the next base is basically starting at the next level. It only goes a short way, and then that, I think that kind of adds up, add 4 to a C, and you get like an overflow of an F, and then that goes to, it doesn't quite go to F there. I'm not too sure there, but there might be a missing chunk there. But there's also a memory map, which kind of shows what's happening. One thing that my current implementation was doing was if you allocate too much of the static memory, it goes over this boundary and into this area here, and if you add too much, then it even goes into the video display, which we kind of saw when we increased it too much. So what I want to do is, the way other operating systems do it is they kind of allocate a page at a time for some concept of a page. My operating system doesn't have paging yet. There's a bug issue, whatever, for maybe putting paging in, but at the moment I'm getting by without paging, and I think I can still get away without doing paging. It's not like I'm avoiding it. It looks actually reasonably easy to do, but I'm somewhat interested in seeing how far you can get without doing some stuff that is kind of considered normal or common, just to see whether it is actually needed. The one benefit with paging is you can kind of have a user mode and kernel mode, whereas everything in this is currently just using kernel mode. So if applications get written and they have bugs in them, then they can theoretically crash the entire system and cause panics. I don't know, if we do something like that, we get a panic. I should probably fix that at some point. Basically, if you push a control in anything, you get a panic. But yeah, so what we want to do is, if we look up std lib, I think that has malloc. So malloc is a custom implementation kind of on top of it, and when we initialize it, we basically just get this malloc heap, which the malloc heap is basically this big. So in this video, I kind of want to go through and get rid of all the stuff that has a capacity like that. So if we look at maybe if we do an underscore, we've got like a bunch of stuff that has a a better grep would be to do a times dot star that. So these are all the places that we have a kind of hard-coded capacity in that we allocate. We basically allocate memory manually, I guess, and that gets assembled into the hard disk. So it increases the hard disk size. So this change will also decrease the hard disk requirements significantly, because we won't have to kind of do all of this. And all the stuff that isn't malloc. So malloc will get its storage from a page allocation, whereas everything else will get it from a malloc allocation. I think that's roughly how it's going to work. So with the malloc, I guess we need to have almost like a set of chunks, because when we get a page, we might not actually have we basically might not have contiguous memory allocated, which, like, say our first allocation might be in this range here, but I potentially will kind of avoid that range and only go into the higher ranges. But I mean, we can actually use that range there, but we also need to work out where our hard disk gets loaded into, and kind of make sure that gets set. And we also need to, there's actually quite a few things that we need to do. I guess, so if we look at codes and BIOS. Let me just close some stuff over on that window and try that again. Disk read, I think. Read. So this function here is so I even did a fix me that shouldn't go past that amount. We can actually work out what that amount is because we know that we're starting from 7E00. So that gets loaded for us automatically, and then this we have to load ourselves. So we can load up like 500k there, which I think that should be alright for our usage. And I think I even did a message. We did magic is at that number there, and so we got 4F, so 1, 2, 3, 4. So magic is at the end of the disk, so we actually have like less than 500k of assembled code, I guess, which is that kind of what I expect. 7 app, it's pretty good, I think. But yeah, so where's this one going? 9FC00. Is that? I think I did this in the last video, but 9FC00. 00FC. So we got 49FC00. So it's somewhere in this kind of range. So yeah, I guess this first usable one is kind of including this. So I think for this change, I'm going to set that to be not usable, which I'll maybe just do manually by setting it to be a reserved after we load it. And then we'll kind of just fall back to this one here, and then we kind of don't need to worry about as like cycling through these, and hopefully I don't know, some systems might have bad memory, and I guess I could like simulate that maybe, but for this I'll just do that. So where do we start? So I guess where do we read it? We don't actually read it in this. That's right. We read it in source boot 16, and we have like an extra little thing here. So we have it includes of memory now. Includes memory. So this is where we basically get all the stuff, and I guess after we go into protected mode, which should be in source boot 32, we do a few things here. So we also have like a stack. So in a future video, I'm going to talk about concurrency type stuff, because I want to get these windows I've worked on to be able to have two windows up at once, and for that we kind of need to have different stacks, which we kind of do elsewhere. But what I should do is make kind of another function which we do this terribly, but extern memory. There's a to do, so we can kind of do it another time, I guess. But what I'm going to do is basically anything below this, I'm going to say is invalid or not usable, and we're only going to start using it from this extended memory for our malloc, which I think is kind of fair, and I think it's probably similar to how we have it. But yeah, I guess I'll just double check that. Now that I've done that, we need to kind of make a public memory init and memory init, and in fact we'll just do it wet for now. And then run it because that's what I wanted to do. So this starts at 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5. Yeah, so that's going there, and it goes up a long way. We've got a lot of addresses there, which for some reason doesn't have these. So I guess it's not possibly mapped, and so we can go up a decent way. No, that's pretty cool. And I guess these devices, these things here, are probably like devices maybe. So it goes from C. Like how many is that? That's problem with that's 4, 3. 4, 3. So B, yep. So that's actually slightly below that. Interesting. I know. I think I'll trust what the computer tells me rather than that wiki page, because this is kind of like a standard bias function. And then another one up there, which is also unusable. So what I think I might do is maybe just take this entire chunk and ignore the whole paging type thing for now, and just use all of that for malloc, which I think is, I don't know, it's probably not, in the future do some paging or something. But in the meantime, what I might do is we're going to loop through this memory descriptor base. What are we doing here? Let me just remember what this is. So memory descriptor has to be an ESI, just because that's how we set up the virtual there. And what I want to do is go through, and while the base high is 0 and the base low is below that number there, basically set the type as not usable. So maybe I'll do that as the first little step. So what we'll do is do some boilerplate, push ESI, and leave and pop ESI, because we're going to be adapting it. And so from here we're going to do kind of similar stuff. So we do kind of want that EBS, because that's the number of stuff we have mapped. Push EBX, so it's very similar to the last one. Pop EBX. So in the loop we'll probably do this. I think that copied. No, it didn't. Then that can be at the end of our loop. Cool. So inside our loop, ESI is at the virtual, so we can kind of test the stuff manually. So what did I say? Basically, If EAX is 0, which we can do with something like that. If it's 0, we want to kind of just continue. I guess I haven't actually done this before, this kind of style, but I kind of like that. Some labels I kind of called the looping increment, but I kind of like the continue aspect because it's kind of what a high-level language would do. So if the base is 0, really if it's not 0, we want to continue, and if it is 0, we then want to check. So we can do the same thing but for base low. And then we can do compare EAX to that number there, which we'll just copy there and set up a extended memory base equals, I don't think I did get a 0x there, so that's that. Extend memory base, and so if we test this with extended memory base, and if it is greater than or equal, then we can go to continue. In fact, if it's greater than or equal, we can probably go to return, just the way things go, because I suppose, yeah, I might do continue, just so we are going through everything, but they are kind of sorted. I don't know if they're guaranteed to be sorted there. Yeah, returns an unsorted list. And rare dodgy cases may return overlapping areas. Well, we'll ignore that for now. But yeah, so it might not be sorted, so we'll check that. But if it is below the base, then what we want to do is move into memory descriptor dot type. Yeah, it was type, and type is that, and I don't know, maybe we'll take type 6. That should fit in. I kind of just want to see whether it is does the trick. So yeah, now we see that it's all 6 until this one, then it's 1, and then it's 6 again, which I'm not sure why, because yeah, these ones shouldn't be 6, they should have been left alone. What I might do is just do this space again, just so we can kind of see the gap between them. Yeah, so that's the high. Right, so the high is all low. We want to do like the high bit is set there, so we want to do a signed comparison, x86 signed, unsigned CMP. I think I've used it somewhere else. Oh yeah, there's JB, that's the one. So if we go here and JB, yeah, so it's same as, I kind of like the other side better. Do we have that? Yep. JB. Yep, that is what we want. Where is a JB when you need one? JB. Right, so jump sort of below or equal, and what are we wanting to do? We are wanting to, we'll take that out, and we are doing a greater than equal. Yeah, so we want not that one. Can we just get control greater? Gosh, there's quite a lot of different types. So the JB is carry flag is yeah, we kind of want an unsigned. Oh, is there a NB? Nah. Oh, above or equal. Yeah, that's spot. JAE. AE. So yeah, it's greater than if it's signed, and it's above if it's unsigned. So if we do this, then those last two shouldn't get changed, and that should be a 1. So yeah, that sounds good. So that is kind of just setting all of the low memory to basically not do that. I think I want to keep that this function at the moment just sets non-extended memory to type 6, which is type 6 is a custom type saying usable memory, I guess. Yeah, cool. What I might do is, just because I'm intrigued, if we run on Kimu and I don't know, like 6 gigs. I don't want to like kill my system while doing this, but yeah. So this one has like another 1 at the end there, and that's kind of where the so this first zero is the high bit. So this is when we start going over into the extended memory, which we can't actually use at the moment because that's like over 4 gigs and we don't have PAE. So yeah, I guess we can just ignore that. That was just kind of interest for me. Right, so we do that memory in it. Yeah, I'll kill that, kill that, and kill that. Yeah, I should be left with malloc. So the malloc. So when we allocate the malloc, when we initialize the malloc, we want to find that chunk of memory. So what we will do is call memory get page, I guess. Chunk. Yeah, we'll call it a chunk for now, and we won't do that. And we will actually need this memory up, a source memory. So here, what we just said was memory get chunk, memory get chunk, and enter 0, 0, leave and ret, and we will probably need the same things just because of the way we do it. In fact, this can probably go to there. Yes, and here, so I'm gonna, yeah, our error case is gonna be that end bit. Yep, we're gonna have that continuing. So here we are going to get the type and then compare it to 1, basically. So that is going to be type, and we're going to compare EX to 1. Memory descriptor 3. We're just going to make a memory descriptor free type free something like that, and do that and that and type free. And if it is free, what we want to do is jump equal to alloc. And we should go to return if that happens. So the alloc can kind of just go here, and it can fall through. Yep. So ESI move ESI EAX from ESI. So that's no, we want to. Oh no, that's not what I want. We want to move that to memory descriptor dot base low, and to do some way to get high memory POE. Goodness, I think there's quite a storm out there. It's just windy today. The weather's been nuts this week, but that's how it is. Right, so that's going to be that, and we're also going to. So we're going to take this entire chunk, I guess. We also need to get the size for malloc, because malloc needs to know the length. I guess we could just return that descriptor, because otherwise we're kind of having to return two things at once. Because this malloc cap we need to not have. So they'll set EAX, which will allow malloc to go and do all that, but we need to get the length out of there, which requires getting two values out. We don't need that anymore. Oh gosh, we don't need that anymore. Haven't gone forward. We also don't need that. Let's just check here. So I've just got the two. So we're going to say that is now used. Memory descriptor type is used. So what were the official types? Reserved, free, reserved, and a bunch of stuff. Yeah, I might just add these. Free, reserved, I can do that. And what's the next one? ACPI reclaim. And that will do that. NVS, don't know what that is, but NVS, I'm sure I'll learn about it at some point. And this one is bad. And this is low. And we're going to have another custom one. Custom types going to be used. Just the way we're going to do it. So we're going to take the whole thing. We need to know what length it is. And that was the thing that we were worrying about before. I think. So this is going to be a void star memory get chunk and int star size. size. It's probably actually going to be a size T, which is just an int in this. Size pointer. So we're just going to return it as a pointer. Pardon me. Right. So size is going to be there, and when we get that, we're going to move. Right. So we can move like ECX to memory to script. No, ECX can be size pointer. And then we want to move to ECX. I wonder if we can actually do this. I'm not sure we can. Yeah, I think we need to do this. EDX memory descriptor dot length. And again, we're just going to get the go back to there. We're just going to get the load it with another pointer, and then we're going to move to where that pointer was, the length that we have, and then fall through to return. Cool. So in this we want to kind of have a how we can do this is this enter. We've used this before. I just need to refresh my memory. Enter. There's a lot. Arg size. stdlib. I think that's even here. Size. Arg size. So here we use like variables, which we put on the old stack. So malloc. So we're gonna basically have one void malloc in it, and it's just gonna do nothing. And how did that go? Args. So it's just the first one, args size. So that basically allocates on the stack our size variable. So now if we like move EAX to size, we can. I think we can just. Oh no, we can't do that. I might need to debug this a bit. Because we're not actually putting that as the pointer. We can step into this actually. ECX size. Don't do that kind of. I think we can do that. That will do it. We can just check in the kernel. So we have this. arg1 is reading it, and arg1 offset is. So we kind of want to not read it. Right, so this is going to be var1 offset and EPP minus. Is that the one? No, it's plus. So we don't need that. nicer to read that in the code. And yeah, I think we do need to kind of move that in. And ECX. I think that might do the trick. I'm just gonna do that just because EAX should return here. EAX is now a valid memory chunk. Yep. Yep. ECX is its size. Cool. We'll do that and just add a bit of white space. Yeah. So I might just run this and see what happens. Right, it breaks. Yes. Alright, why can't we do that? Like it likes it there. EBP, yeah. Looks a bit gross, but I think we need to manually do this. Right, so move ECX to EBP, sub ECX, var 1 offset, except we want to add. Yeah, we can't do that. Sub ECX size of malloc chunk. Right, we don't have that. Where do we? Oh, we don't really define that anywhere. I think I'll just do a dirty hack and extern memory get chunk. This should be in an include file. Alright, so now it just runs and doesn't really do much there, which kind of means that things aren't working. And what we can do is, yeah, that malloc heap was used, so I think this will, malloc heap. Yeah, so we want to we want to get the kind of start of it. So malloc heap is now just going to be a dd of 0, so that's going to be a pointer to first chunk, and each chunk has the next chunk on it, so each chunk has the next and it also has the previous. So when we initialize it, what we can do is move to the address of malloc heap EAX. So that's going to be the valid hunk, and if we ever need to like grow it, we can in future we can kind of just get a new chunk and then grow like that. But I don't know, at the moment we're just kind of allocating all memory that we possibly have. Right, so here we get the so what we want to do is see what is there at the moment, and if it is so if it is equal to 0, yeah, we want to. Oh, we don't. Oh no, we don't. Yeah, we want to read that, and we don't want to do that. We want to basically test EAX, and if it is not 0, we want to initialize it. Yeah, and then here we'll do the same. What size do I? Oh yeah, that's just checking that we're getting a valid size. So we don't actually need to do this again, do we? I guess. Yeah, it should kind of theoretically return it. Oh, no, that to do can stay. Let's run this again. Cool, that does some stuff. That gets a panic though. Not a great panic. Unexpected return from KMan, which suggests that, and like looking up, we can. Yeah, so it's when we're getting the chunk. So we're kind of overflowing here, and the type is a large number. So what I might do is jump into the debugger. For that, I find it easier to have another window. So if we do debugger, and what we're going to do is break on malloc init. We're in that real mode, but that's alright. Might just change that back. Debug that one. Yeah, that's where we're like doing that thing, but I guess it doesn't really matter. I mean, it sets this architecture, but yeah, if we do that and do that same break and then continue, yeah, we should just jump straight to there. Cool, so we're in this malloc init. We're going to step into this. Right, so here's where we need a kind of EBP is that thing there, and hopefully that goes down a little. Well, the ECX does. So EBP is D4 and D0. So we've gone down from EBP, which is basically up from the stack frame, because the stack's kind of in reverse. That makes sense. So now we're looking at, and yeah, say if we look at what EBP is, that should be kind of a return pointer. No, that's not what we want. We want to look at what is in there. Just got itself. not sure that's how it's meant to work. Oh no, that's a C there. Yeah. So that is pointing at the last stack frame, which if we look at 4 above it, yeah. So that's our return pointer. So if we look at BT, that is our return pointer. So that's where we're going, and EBP, that is our last stack frame. And if we look at so ESP is basically where our variable is, and it's currently 0, and it is db0, which is higher than so it's kind of below the stack point frame start. So it's not going to overwrite stuff. That is how we want it. So the value was 1db0, so that's our pointer. So if we go into get chunk, we push those things out, we clear that, and then we start looking at the memory base, and it was like the 5th one from memory, but we can see in EAX that's our type. So we've just allocated the first type. That doesn't seem right. That does not seem right at all. We already printed source boots feels like a race condition between this term in it. So I think the memory in it has to be done quite early on. In fact, potentially the very first thing. In fact, potentially it could get done in first thing of the boot 32. It should call that function to kind of clean up stuff. And I think I'll just give that a run, see if it works. Right, we've still got the same thing, unexpected return. So what I might do, I'm going to break on that, and I'm also going to break on memory init. So that should hit first, cool. Memory init is this one here. So here we checking whether we've run out. So EBX is how many descriptors we have. I think no, it might not be that. Right, so here we get the base high, which is 0. So we then look at the base low, and the base low is 0 still, so it is less than that, so we're going to set the type to be 6. I suppose the 6, that can be, what do we call it? We call it low, that's right. And then we get the next one, and so this one is still low, I think, yep. So we'll set the type there. This one is still just low. This one is now on the high, so that should just skip to that. And EBX is 2, and so we should have like a couple more This one is also high, so we'll leave it untouched, and this one is also high, so we'll leave it untouched, and then we've run out, so we'll return. That looks good, and we like pop everything. Right, so now if we look at the malloc in it, we get all that, and ECX is 1DEB0, so that is our, in fact, what I might do is DW int star and that's going to be 0x1DEB0. No, we didn't want that star. Yep, and then display that first one. So that's going to be our hopefully size of what we have. And I might do it as a hex as well. I think that will be useful. Right, so now we are not in the init, we're in the getting a chunk. Where am I looking? Yeah, getting a chunk. So here we push EBX and ESI, we clear EAX and we get, so there's 6 pointers and we start there, so we shouldn't be ending. Here we're going to get the type into EAX, it is 6, so we should get the next one. Here we'll get the next type. It's 6, so we should get the next one. Here the type is 6, so we should get the next one. Here I think the type is 1. Yeah, so the type is now 1, so we should go to alloc. Yep. So we're going to move the type to be used, and used is L1, so that's going to be a 7. And then we're going to get the size pointer. Right, so this is still the same, and then we're going to get the length into EDX, so that's like a lot, and then we're hopefully going to move it, and so it should show up down here. Yep, so that looks good. We have returned via a pointer, and here we are getting the base low into EAX, which that looks about right up the top there, and then we're going to reset those because that needs doing, and then we're going to be here. So we've called that. We'll just reset stack. Right, so here we're going to get E6 being the size, which that looks good. That looks exactly what is in memory, so that looks good. And we're going to take off a bit of stuff because that's the size. Basically, malloc takes up a bit of housekeeping. So EX is at that level. What I might do is yeah, 1 over and like 20. Right, so that's like kind of what it looks like at the moment. So we're going to set it that chunk to be used, not we're going to set the length to be that, and the next to be null, and the previous to be null. And if we do that, right, so I wonder if that length is good. Yeah, it's kind of like off by 1. Wonder if that's actually efficient. yeah, so we 7EDFF3, and the used is just that byte. Need to look up this again. Yeah, so used should just be a byte, so that should be those two there. And then that is the length, which is a word up to that one there, and then the next is like there to there, and then the prev is there to there. Yeah, it's not like the best, but that is all right. Right, so at this point here we have edited it, and what I might do is x malloc heap. So that should be 0 at the moment. That is correct, and at this point here it should turn into 1,000 or 100,000, which seems right. So we leave that and we reset the thing. So we're back in malloc. So we've just called malloc init, and EAX is basically as if we've read that malloc heap. And so it is that address there, and that is looking right. So now we're trying to allocate some size, so we're trying to allocate that much size. I might display all of that because I'm fairly confident that's doing it. And we're going from like a high spot. Yeah. Right, so the size is a legit size, it's not 0. And so now we're in the big loop. Do we have a valid pointer? Yeah. Has it been used? It has not. Is the size enough? It should be. So now we'll jump to the alloc. And we do all that stuff, and there's like some debugging stuff we can do, but I'm reasonably confident that did the right thing, but if need be we can dive further in, and we reset those. So I think I might want to just break on malloc itself. So we get that base. It's been initialized, so that's all good. We're trying to get a bunch more data there. In fact, this one here. Do we still have our malloc stuff commented out? No, we don't. Most P of this file, malloc. Yeah, that's the one we want. Sure. Used equals 0. Set dollar size equals 1. This was done before I had debugging symbols, so there might be a better way to do it now. Equals 9. Display db EAX plus $used. That doesn't seem right. And size. That might be right. Yeah, that is right, because it just knots it, so it's the whole thing. Then x of star of $EAX plus $next, and then the same for prev. Cool. so we're in the loop. We're trying to get a valid size, and so yeah, it shows us all that quite nicely, and that's the size that we're trying to get. So 4096. This one is a valid chunk, but it has been used, so we'll go to the next one. So it should set EAX to this value here, 10280D, and 10280D. Cool, so that got the next one. That's a valid chunk. This one is not used, and it definitely has enough to fit our 4090. So we should, we'll jump to Alec, and here you can kind of see the magical happening in the Alec. So we set it to be used, so it changed that to that, and then we kind of split it. So we'll store EBX, store the current one, and then we'll get the length of the current one, which is quite giant. We'll take off the size of, so EDX has the current length of it. We'll take off a tiny chunk for the mallet overhead. Now what do? We take off the size that we're trying to get, so this amount here. Yep, that looks good. We see whether it's still valid. We see if there's enough space for a split. So yeah, there is space for a split. So now we get the next pointer of what we are, which is nothing. So theoretically, if we do a free and do another mallet later, that will fix itself. Alright, and then we add the size that we're allocating to our current pointer, so that's going to be like our next one. So here's where it starts getting a bit more corrupt. Then we add on the size of the mallet overhead, because we need to do that. And at this point, we had stored EDX as the size of the split thing, so that should set that split to be that, and then we should set the next, which is 0, and we should set the previous one to be the chunk that we're allocating at the moment. What are we doing with that? And then we're getting this, which is going to be the next pointer for the chunk that we're allocating, and we'll store that in ESI, and then we'll get the old chunk that we're going to return back. So that's the one that we just set there, and the size is what we wanted. So now we set the size to be what we're allocating, and we set the next to be that one there, and then we add on the offset because we're allocated something, and we return. It's looking good. And it's like printing out stuff. So what I might do is, if we go here, and we'll just continue each time and kind of see where it breaks. And here we can kind of see what it's allocated. So we can see that 7 is, we have used that chunk there. I'm just at a loss. I don't think I changed anything, but it's just working now. Like when you run it, I'm at a loss. So if we just debug it and run it, it that works fine. If we run it, we get unexpected return. Now, did we tools run? What are we using there? Kimu. Kimu. So we set 3 gigs. So what do we set for debug Kimu GDB? Oh, that's done in GDB init. Yeah, so this, I know if we do 3 gigs there and then do a debug, turns out having too much memory is bad. So if we run this, now we get yeah, so that's good, believe it or not, because now we can do the same. So if we just break on malloc and move that over there, we can hopefully see stuff and see where it breaks. Right, so there, that looks like a bit of corruption. And yeah, all these types are just way off. So I think where we're is that like gone over 1 2 3 4 1 2 3 4? Nah, that is still definitely under. So that magic has gone down quite a lot. But yeah, this this type has like gone down ridiculously. Like those types should not be that high, and then it returns there. Cool. It's somewhat workable. So yeah, it turns out if you go to that, turns out if you have too much memory, it breaks. So we'll break on that, and we'll break on that, and we'll also break on malloc, but we should get memory in it first. Memory init, this one here. So here we should have 6 things, and we're going to have a bunch of things. Yeah, I might actually, it kind of comes out in the works while we do this. So we haven't done anything yet. So now we set the base low, and it is low. So we the base high, and it was low. So we then check. Yeah, that's right. Then we get the base low, which is also 0, so it is definitely low, so we set the type of it to be low. And where are we looking? We're in ESI, so it's writing at that point there, which, yeah, I would kind of expect to be all legit. But at some point, oh man, I hope we don't have to do like a memory watch point, because that can be quite painful sometimes. But it's just really slow because it's checking lots of things. Right, so we jump to the start, then we get the next one, so it's still low. We get the next address, that is 4, so that's still low, so we should be setting that like that. still low, but now this has gone up a little. 4, we're still low, so we should set it a bit. Here we've just reached the high memory, so here we shouldn't set it, and we'll still have a look to see if there's more stuff, because it might not be in order. Right, so that is real high, and it doesn't set it. That's good, using the right thing. And that's also, and we also skip it, and that's all of them. So I'm happy with that, and yeah, we should return there. And then it does like a bunch of things, but we'll see where malloc gets called from. It gets called from term reset. So the first thing malloc should do is it should see that is not initialized, so it should jump into init. So the stack pointer is there, which, yeah, I wonder if, yeah, I don't know. So in this, when we're getting a chunk, we're getting a chunk, so we get the same thing. We should still have 6. Then we check whether the type is free. It's not, it's our 6 type. So we get the next one. It's still 6. It's still 6. It's now free, so we will allocate it. So we go down there, we set that type, and ESI is still like real low, so it should be legit. Yeah, what? I wonder. Yeah. Right. Anyway, so then we get the pointer, which is still that 1db0, and we get the length of this thing, which does have the high bit set. So I wonder if that could be it, because I don't think it did when we had less memory. We set that into the pointer, and we set that to be our base, which looks legit. I'll just set up all these displays again, because we're doing malloc-y things. So the malloc, so we've got a chunk, we're still in it. We get the size that we got given, that looks good. Yeah, so I guess the size is unsigned, but yeah, so I think that's the bulk of our problem. So this number should basically go down by D, so that E as a unsigned type thing, whereas I think it's doing it as a signed thing, so it probably won't do what we expect. Did go up as a sign. Oh, yeah, the sign value went down. I think that's right. I wonder if we can. sign decimal U. So that's like the actual size. So it's probably in our splitting that it gets into weird things. Love the old sign, unsign. Cool, so here we have got it. We are looking for 1024 things. Slightly more, 10 times more in fact. Valid size, so we're in the loop. We should scroll up to the actual loop. Alright, so we have a valid pointer. It's showing us some stuff. It is currently not used, so we should be able to take it. And the size is good. Or did it not think the size was good? Yeah, there we go. So it didn't think the size was good. So we wanted that much, but we were comparing this number against it, and then we now look. Yeah, cool. That is the bug. So less than was B below. So if it is below, if it is below, do we have any more jumps? Comparisons. Yeah, I think that should do it. Try and give that just a run. Yeah, cool. Look at that. Just works out of the box first time, and it does stuff. And we can still scroll. Man, I forgot it bit to my ear when I did that. Yeah, we can see that we have used this. Yeah, this is looking good. Oh, that's the beat there. Right, cool. So we fixed that. Cool. So what I might do is, while we're here, just commit up this stuff. It's a good rule of thumb for assembly is if it's been tricky, you should commit as soon as you get it working well, before you start on the next piece. Otherwise, it can get a bit hairy. So let's change to our alec init stuff. Yep, that looks good. We change our test for our initialize. We don't need to do that. And then we check the actual unsigned stuff. We don't have the capacity, and then in our memory handler we set up a bunch of constants and some things, and we add a couple of functions. So we do the init and the get chunk, and I think I might add that in as well, and may as well. Just so the debug is using the same amount of memory as the non-debug, the running. Cool. So lib sdd lib get malloc to use actual memory. Cool. So now my next thing was if we do the git grep for what was it, times.star cap. So all of these things I think we can now change to basically not use this times. So yeah, could just use malloc. So where do we use debug symbols? It feels a bit like hacky, but yeah, so I guess we need to do a similar kind of lazy load that if it hasn't been set yet, then we need to initialize it. So I think that's just going to be the pointer to like an array. Pointer to array of learn to type dd0, and this is going to be a pointer to the string. Pointer to array of strings. In this capacity, initial right, so the first thing we're going to do is get this debug symbols, and we're going to compare it to 0, and if it is equal we do like a bunch of stuff. Yeah, I think I'll do the same thing. So if it is not 0, then we'll go to initialized. I was thinking I could be good in and I guess we need a capacity. And we are using malloc. Where'd we go? Debug add symbol, wasn't it? Yeah. Debug symbols debug symbols in it, and here we can make it to 0. And we're basically going to do some mallocs. So first thing we're going to do is, I guess, get this. What was it at the end? So it was for so it's basically word size times debug initial cap. Malloc of word size times the debug initial cap, and then once we get that, we should test EAX and jump 0 to error. Error can be here and public panic. Bad, I guess. And if it's all good, then what we should do is move two debug symbols plus 2 times word size. EAX. And then we're going to do the same thing except 3 times, and then finally we're gonna symbols plus word size, and we're gonna set that as debug initial cap. So that's gonna be our capacity, and then we're going to we'll probably jump return. Cool. That looks good. Right. So we initialize it, and then we get this. So what we want to do is, I guess, move the current and then in the overflow we could think, and I think I might. Yeah, cool. So we get that, and then we. Oh, right. Yeah, this is a bit different. I'll probably pick the worst one to start with. So that's our current thing, and yeah. So what I might do is edx debug symbols plus word size 2 times. Feels like its structure would be better here. I guess, do we use C? No. Where do we actually save it? Debug word start and char star strip. That just lets the formatter know that goes there. You know what? I might. I might not do this. It's probably the worst one to start with, but yeah, I'll do all of those in a different video. I feel that it's probably better, and I'll probably start with some easier ones that aren't that kind of should have been in a structure, and the same thing in this STDIO buff. Potentially I could leave all of them actually, and then just address them as I'm kind of touching those files, because this that kind of area is a bit hacky at the moment. It's used to do backtrace, but yeah, I think I will leave it at that. I think that's good kind of pause spot. So we got basically using proper memory, which I'm happy with. We do kind of just allocate all of the memory to Malik, then Malik then divvies it up a bit more. So in future we could kind of get a smaller chunk each time. But yeah, I think that's probably good for now. And yeah, it still works. Had some bugs before, but hey. And yeah, that's gone down quite a bit. I'm actually interested if we if we run an old version. No, we kind of needed to get yep, that, and just head one less. And so before the change that we did, so our magic was at 5, and now it's at 1. So I think that is a remarkable lowering of our hard disk size, basically. So if we look at I don't think that's gonna like that. Yeah, there's an endless loop. It just runs forever. Yeah, so we're not using all of that, but basically if we minus off the 7E00, we can kind of see our hard drive size, which, yeah, but we were using quite a lot. It doesn't quite seem right. Oh no, that is good. Yeah, because that 7's like one more over. Yeah, cool. Anyway, I'm just sidetracking. Yeah, so it's a good place to leave it. And yeah, hopefully you enjoyed watching this video, and let me know if you liked it, and I'll pump out some more videos in the coming times. Should be fun. So yeah.